Hello, everybody. This is Miss Peachy from WCA Physics A, and here we are today in Unit 5, Lesson 3, Energy Transfer. Our keywords are energy flows, kinetic energy, law of conservation of energy, mass, potential energy, velocity, and work. So let's go ahead and delve into this, shall we? So we're really looking at how energy flows from one type of energy to another, and how within this, energy can be converted from one kind to another, and it can be used to do something called work. So it starts off talking to you a little bit about cannons, and how when you look at a cannon, for example, the cannon will launch, and when it does, the cannonball comes out of the front of the cannon, and the cannon itself kind of recoils backwards as well, right? So we can understand a little bit about the relationship. Before the cannon launches, before it is shot off, there is potential energy in the form of the fuel within the cannon itself, the gunpowder that is used to ignite and launch the cannon, right? So this potential energy can be converted into energy of motion, and that motion is the motion of the cannonball and the motion of the cannon. And they actually have opposite directions that they're moving, right? The ball kind of comes out the front, and the actual cannon recoils backwards. And basically, it tries to explain to you using some math and a simulation, because it's going to have you do a little simulation down here using an Excel program, that if you change the mass, so the more massive the cannon is, the less velocity the cannon is going to have. And the lower the mass of the cannonball, the more velocity of the cannonball, right? So both of them are moving, so both have energy of motion. And energy of motion is kinetic energy, 1/2 mass times velocity squared. So we can say that the kinetic energy of the cannon is 1/2. We'll use the big M because we're talking about the big old cannon, times the velocity of the cannon squared. And if you add that to the energy of the cannonball, which we're going to use little m to represent, and little v, and I'm going to write my little v just a little different just so that I don't mess up, that is going to equal, we're going to use big E to represent the total amount of energy, right? So if you think about it, the energy that is found inside that fuel to start with, inside the gunpowder or whatever is used to fuel the cannon, has to be equal to the sum of the potential energies of both, or the sum of the kinetic energies of both items, the ball and the cannon itself. Then it says, you can simply rearrange this equation to come up with these two equations where the velocity of the cannon is equal to this and the velocity of the cannonball is equal to that. I will say you cannot simply rearrange the equations to come up with these two equations. There's a lot of more complex math that happens here that we won't be delving into because you don't really need to know how to do it, and it's going to be kind of confusing as well. So we'll just take it at face value that you can, through a little bit more complex mathematics, solve for the velocity of the cannon and the velocity of the cannonball. And you can use then the Excel program or whatever, if it's Excel or Google Sheets, you can use to actually create a spreadsheet to kind of show these variables, which we're not going to do here. We're just kind of going through the concepts. We're not going to be going through every single little thing that they do within the lessons themselves. The other thing that's kind of a bit confusing about this lesson is it talks a bit about momentum, and we have not gotten into momentum yet. When you go to the course outline, you will notice that momentum is Unit 6, and here we are in Unit 5. So it's talking about something you have not had yet, and that's, I don't know, it's out of order in this respect. So it says the following assumptions can be made. The total momentum of the cannonball and the cannon are conserved. We can also say that the total amount of energy is conserved as well. So law of conservation of momentum, law of conservation of energy are kind of equally applicable in this situation. We're going to ignore air resistance and friction. It says the energy from the cannon blast is transformed into initial kinetic energy in the cannon and the cannonball with no energy lost to any other sources. So we're not going to worry about energy being lost as heat in this situation or anything like that. We're just going to ignore that part of it to make things simpler. A lot of times when you're doing models, you need to kind of make things a little simpler. So that's what we're doing here. So those are kind of some of the states that they're talking about here. Essentially, what it boils down to is that if I have a larger cannon, I'm actually going to switch this out and use my handy dandy pen. So I'm going to call this a larger capital M, right? Because that's our cannon. Then the cannon itself is going to have less velocity. And the same is true on the other side. If my cannonball is smaller, so if I decrease my little m, now I'm going to write it as a downward arrow to let you guys know that means decrease in my shorthand. Then what's going to happen is the velocity of little v will go up, right? So they're kind of inversely proportional to each other. If I increase the mass, the velocity goes down. If I decrease the mass, the velocity will go up. The other thing that they talk about in this lesson is that this, let's see here. They talk a little about something called work. And work is moving a force over a distance, right? So I can do work on the pen in my hand by picking it up and moving it. I'm using a force to pick up the pen and move it over a distance. Therefore, I am doing work on it. Energy is the ability to do work, right? It has the ability to do work. So I have energy that has the ability to do this work. If my thing, it's kind of easier to understand in my opinion, is if you think about a moving object. If my pen is moving, it has the ability to do work. The more it moves, the more work it can do, right? Think about, say, I don't know, think about a wrecking ball. So we're going to draw a crane, and we're going to put a wrecking ball on the crane. And that swings back and forth, right? It's going to swing back and forth to kind of destroy a building or knock down a wall or something. The more it moves, so the faster that ball is going, the more destructive power it has. It can actually do more work on the building and knock it down. If it's more massive, if it's a heavier ball, it can also do more work. So the force that the ball applies is much, it can move the building a distance. It's doing work on it. And the amount of work it does depends on how fast it's moving and how heavy it is. That kind of harkens back to energy. Energy 1/2 mv squared, right? So kind of see the relationship there between work and energy. When we are looking at our cannon, in our initial cannon, the cannonball that it is firing has some energy right away. So let's go back to talking about potential energy and kinetic energy, right? If we have somebody just dropping a ball, say we just hold this ball, that's a bad picture, guys. I don't know. I'm just going to go back and try that again. All right. So I'm going to have somebody holding this ball, whatever. And we're just going to drop it, and it falls. At some height above the ground, right before you drop it, it has potential energy, gravitational potential energy, right? Once it hits the ground, right here, right before it hits the ground, it's at max kinetic energy. Does that make sense so far? It's kind of repeat. But let's say instead of just dropping it, I threw it down. I actually gave it energy as well. If that's the case, you have to take into consideration the initial amount of kinetic energy it has. So the amount of kinetic energy it would have when it hits the ground here should be equal to the potential energy when you started. Remember, they're equally, one is converted to another. Here we have all potential, no kinetic. When it hits the ground, it is all kinetic, no potential, right? So that's true. However, if I dropped it, instead of dropping it, if I threw it, I also added an initial amount of kinetic energy. So my total kinetic energy when it hit the ground is not going to be equal to the amount of gravitational potential energy, but actually it's that plus how much it started with because I threw it, because I gave it a little boost to start with. So once it hits the ground here, it's actually going to be having a bit more energy than just dropping it alone because you threw it. So you have to add those two things together. You have to add the gravitational potential energy plus the amount you pushed it or you threw it, the little bit extra boost you gave it, and that'll give you the final amount of kinetic energy. If I take the initial kinetic energy minus the final, so if I subtract out what I pushed, it tells me how much work that I did on the ball. So I think it's kind of, honestly, I feel like it's a little bit of a circumvental way to say literally this initial energy is just the amount that I threw it, right? That's how much I gave it. And you have to take out what the work that gravity did on the ball. How much work I did on the ball is the difference between the amount of kinetic energy that was from the gravitational pull and the amount of kinetic energy that I imparted to it with my push. Because I'm moving that, I'm pushing that ball a little bit more. Okay. Then finally in this lesson, we're going to go back to, get some examples here. We go back to other types of energy. So we also have heat energy. And heat energy is just a different kind of energy, right? Heat energy is associated with molecular motion within a material. So everything is made up of atoms, and those atoms and molecules are moving around. And the more they move around, the more energy that's in the item. We can measure the average kinetic energy in something by recording its temperature. And heat energy will always flow from areas of high temperature to areas of low temperature. So if I have a hot cup of coffee, it's always the heat's going to flow out of it, and it's going to cool down the coffee and heat up the air around it. It's never going to flow from the cold air to the coffee. So my coffee isn't just going to sit here and get warmer and warmer. I wish it would. It only gets colder and colder as it sits here. It also talks about how the greater the difference between the two things, the higher the flow of energy. So if there's a profound difference, if you have a really hot object and a really cold object, the energy transfer it'll flow quicker. It'll flow, have a greater energy flow. And then finally, this part of the lesson talks about something called R values, and that's where you're going to be doing another kind of graphic model here. And it talks about how insulation in the United States is rated by R value, and R value indicates how effective the insulation is. The higher the R value, the better the insulation. So you're going to use the data in this, follow the step-by-step directions to be able to create a model to determine the R value of insulations. So I'll let you go ahead and do that one on your own. If you have any questions on that, let me know and we can kind of meet in live lesson and go through it. But it's pretty self-explanatory if you just follow the steps there. So that's pretty much it for this lesson. Just energy transfer in general. Remember that there is a relationship between mass and velocity with kinetic energy, right? If you increase the mass, the velocity has to go down in order for energy to remain constant. And if you decrease the mass, velocity goes up to have energy remain constant. That energy is the ability to do work. That if you have an object that's not falling, but you're actually giving it like a boost, a push, or you're firing it out of a cannon, that the kinetic energy that the object has is equal to the amount of kinetic energy when it hits the ground is equal to the amount of kinetic energy it got from falling. So that's basically or opposite the potential energy it had at the top of its free fall. But also you have to add the push that you gave it. You have to add that extra energy to it. And then finally, we talked a little bit about heat energy and how heat energy is the measure of the motion of the molecules and atoms inside of something, and that heat energy always flows from high temperature to low temperature, and the greater the difference between the two temperatures, the greater the rate of energy flow, and that insulation is based on something called R value, and the greater the R value, the higher the insulating effect of that insulation. That's everything in this lesson in a nutshell. Let me know if y'all have questions. Otherwise, I will see you in the next one.